Okay, welcome back from fall break. We're going to be getting into our next topic today on electron configuration. And I've already explained probably why we're watching this video together. This is one of the more confusing and complicated topics that we're going to get into. And so it's probably best if we watch this together so that we can pause and you can ask me questions as I'm explaining things. So let's talk a little bit of review. So before break, we had started to explore what the inside of an atom is made of, right? Like what are the things that make up an atom? And we had talked about isotopes and average atomic mass, but today we're going to get into some really nitty-gritty details about electrons specifically. Okay, so let's just review what we've learned so far. We know that protons and neutrons are in the center of every atom. They compose what is called the nucleus, right, of the atom. So protons and neutrons are in the center. But where are the electrons exactly? I mentioned before that we were going to get into this later in the course, and here we are. So we are going to talk a lot today about where electrons are and how they behave. The short answer is it's really complicated. And so what we're going to do is we're going to get into the long answer starting right now. Okay? So here's our objective for the day. We are going to be learning how to represent an element's electron configuration in both standard and noble gas notations. We'll talk about that. And we're going to learn how to construct Bohr models of atoms based on the electron configuration. Okay? The electron configuration of an atom is just where the electrons are. Okay, and so we have to learn, first of all, how electrons behave, and then we also have to learn how to actually write down this thing called the electron configuration. Luckily for us, actually doing this is not that hard. What is hard is learning how elements behave. And so that's why we're watching this video together, because a lot of this is just kind of confusing, and it's best if we can pause and ask some questions as we're going to avoid as much confusion as possible. Okay? So, look at this guy. He's got a real nice look on his face, doesn't he? We'll talk a little bit about him. Let's talk about electrons, okay? So, typically, we, and by we I mean like humans, okay, not scientists or chemists, but just humans in general, right? We tend to view everything in our world as like a physical object. Okay, so like think of a football or a basketball, right? If you throw a football or if you throw a basketball, we know where the object is, right? Its position and its momentum. Momentum just means like its direction, where it's moving, how fast it's moving, that sort of thing. So typically we view everything in our world as like a physical object, right? Basketball, football, coffee cup, regular cup, all the different physical objects out there, like that's how we view the world, right? We can interact with things, we can touch things, pick them up, throw them, drop them, that sort of thing. With electrons, we have to be a little bit careful, okay? And that is because of starting about 100 years ago, actually more like 120 years ago at this point, some scientific discoveries by this guy, Max Planck, and others, taught us that not all objects can or should be thought of in this way. So we can't think of all objects or all things as being physical objects, like tangible, hold on to it, we know exactly where it is and how fast it's moving. Things get a bit complicated, okay? So for very small pieces of matter, okay, very, very small pieces of matter, like electrons, okay, and you'll recall from before break, electrons are the smallest subatomic particle, right? Protons and neutrons are also very small, but electrons are like way smaller than that, right? You remember looking at the mass numbers or the masses for those different particles. Electrons are very small, right? So for very small pieces of matter, like electrons, they behave differently than large objects, okay? And even protons and neutrons, which are small, are large enough to be thought of as normal particle-like objects. Okay, so for today, we really are only talking about how electrons are different and how we have to talk about them. Protons and neutrons are small, but even they are big enough to treat normally, okay, to treat like everyday objects. Electrons are different, okay? So rather than behaving like small particles, okay, so if we go back to this image here, right, rather than thinking of electrons like little tiny balls or little tiny particles zipping around, we shouldn't think of them that way, okay? Electrons behave more like energy, all right? And you probably don't know a whole lot about energy. I mean, I'm sure you've heard of the term energy, but what does that even mean, right? What does it mean to behave more like energy than a particle? So that's kind of what we're going to get into today, okay? And that's why this topic can be so complicated. The theory of how electrons and other very, very small particles behave is called quantum theory, okay? Quantum theory, and I'm sure you've heard of this word as well. And it is very, very complicated, okay? So we're not going to be diving into every detail of quantum theory, all right? What we're going to do is we're going to learn a little bit about it, and we're going to use the implications of the theory to help us understand how electrons behave, okay? So we're going to get into it a little bit, but you're not going to be responsible for knowing everything there is to know about quantum theory, okay? So the first thing that we should understand about quantum theory and about electrons is to understand what this word means, okay, quantum. All right, if we can understand what this word means, that's going to help us a lot, all right? So what does the word quantum mean? I'm not just going to give you a definition because that's not going to help. Instead, let's talk about these two words here, okay, continuous and discrete. This, if we can understand what these two words mean, then we're going to be able to understand what quantum means, all right? So two vocab words here, continuous and discrete. These are kind of opposites of each other, all right? And these are two definitions. Something that is continuous is forming an unbroken whole without interruption, okay? Something that is discrete is apart or detached from others, separate or distinct, okay? The best way that I like to give students an example of the two different terms here, continuous versus discrete, is like if you were measuring something, okay? Let's say you were measuring the length of your finger. Okay, so you have a ruler, right? And you hold the ruler up to your finger, and you're trying to measure the length of your finger. It's kind of hard, right? Because first of all, where does your finger start or begin, right? Is it like right at the knuckle or a little below, or, you know? But putting that aside, okay, if you're measuring the length of your finger, maybe it's, I don't know, 2 or 3, 4 inches, something like that. Think about this, right? Think if you zoomed in at the end of your finger, and your ruler also zoomed in. You know how there's like little marks on the ruler, right? Well, think if those got even smaller and you could see more marks, right? Maybe you say like 3.5 inches, but maybe if you zoom in a little bit more, well, maybe it's actually more like 3.6 inches, and then if you zoom in some more, maybe it's more like 3.65, and maybe if you keep zooming in, right, keep zooming in, maybe you can get finer and finer detail, right? You can keep putting in those decimal places. Measuring the length of something is like a continuous type of measurement, okay? You can keep zooming in and you can keep getting more detail, right? And it's kind of like a never-ending process, right? You just sort of, you could imagine just keep zooming in, and I mean, obviously you would get to a point where you can't really zoom in anymore because you don't have the tools, but that number, okay, the length of your finger, that number or that measurement is kind of like a continuous number. You can keep getting finer and finer detail, right? Let's contrast that with a discrete measurement, right? How many fingers do you have? 10, right? Thumbs count. So you have 10 fingers, right? You can't get any more detailed than just 10, right? I mean, it's literally 10 fingers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's it. That's the difference between something that is continuous and something that is discrete. Discrete things are apart or detached from others, right? So I've got my 10 fingers, separate, distinct. Something that is continuous, if you were to measure it, forms an unbroken whole without interruption. What that means, right, is that you can sort of keep zooming in, keep getting more and more resolution, and it's just it's a continuous number. It's a continuous thing. You can keep zooming in and getting more and more accurate the closer and closer you look. Whereas for something discrete, you can't, right? You can just tell, boom, I have 10 fingers. Okay. Now, lucky for us, we're more concerned with the second term here, okay? Discrete, all right? I understand continuous is still kind of complicated to understand. Discrete, not that complicated though, right? You have 10 fingers. What Max Planck discovered, that was that guy on the previous slide, he discovered that all energy is quantized, okay? And what does that mean? Well, quantized, that just means that energy is discrete, okay? It comes in discrete amounts, okay? Separate, distinct amounts, all right? It's not a type of thing that, you know, you could keep measuring forever, get more and more accurate. It's actually set, distinct, discrete amounts, okay? And this matters a lot for us, okay? Because electrons behave like energy, okay? They don't behave like particles all the time. They do sometimes, but they behave a lot more like energy, and energy is quantized or discrete. So here's what this means for us, okay? If you take one thing away from the last 5 minutes, it should be this, all right? Electrons exist at discrete energy levels, okay? So where are they inside of atoms? They are at discrete energy levels, okay? They can gain or lose energy and move between energy levels from like one energy level to another, but they always exist at discrete energy levels, not in between, okay? So let's take a little bit more of a look at that, all right, and try to understand that even better. This guy, Niels Bohr, working around the same time as Max Planck, developed the first model for atoms with this quantum idea in mind. Okay, he developed a model for how we can think of electrons inside of atoms. And this is referred to as the first quantum mechanical model of the atom. Okay, so right here, what we're looking at right here is called like a Bohr model of an atom. This center part would be the nucleus, okay, so the protons and the neutrons would be here. And this green thing, or these green things, represent an electron, okay? Obviously not to scale, okay, because the protons and neutrons are a bit bigger than the electron. Can't really tell that from here. So this is just sort of a model, right? But that's what we've got going on here. And these yellow rings are, they're referred to as orbits here. I don't like that term. This is not my picture, okay? But these different yellow rings are the energy levels, okay? And so what we just discussed, right, was that electrons exist at discrete energy levels. Your electron or electrons can be here at this first energy level, or they can be here at this second energy level, or here at this third energy level, but they're not going to be in between, okay? And that is how electrons behave. That's what we mean when we say electrons behave more like energy than they do a particle, right? If you were here and you threw a football from here to here, the football would have to travel, you know, from this energy level to this one. It would have to like go physically from here to here. You could take a snapshot and you could find it in between, right? That would be something that acts like a particle or like an object. Well, electrons do not behave that way, okay? Electrons are either here or here. So one moment they can be here, another moment they can be here, or another moment they can hop back up again, okay? That is how electrons are strange, and this only happens with very, very small objects like electrons. But as we're going to find out, electrons are basically the most important thing when determining how atoms overall behave. And so we have to understand this aspect of electrons in order for us to understand how chemistry works. Okay, electrons are super important. They are the dominating factor in terms of how chemistry actually works. So let me go back to the slide here. This Bohr model shows us that electrons aren't just flying around the nucleus in random ways. Instead, they exist at these fixed energy levels and can hop from one energy level to another by gaining or losing energy. In order to go from this first energy level to the second energy level, the electron would have to gain some energy, okay? And then in order to hop back down, it has to release energy or lose energy. That's what this little red line is symbolizing here. If an electron was to go from the second energy level to the first, it would have to give off sort of the difference in energy between these energy levels in the form of light. Okay, we'll talk about some of that at a later time. Okay, so since then, many refinements to Niels Bohr's quantum mechanical model of the atom have taken place. His original model was not completely correct, not perfect, but the fundamental idea still holds. Okay, electrons do exist in atoms at particular energy levels, and they can hop around between those energy levels by gaining or losing energy. Okay, and our job is to learn how to describe where the electrons are inside of an atom. This is called the electron configuration of an atom. Okay, so if I were to go all the way back to that first slide on the objective, right, we're going to learn how to write down the electron configuration of an atom. Where are the electrons? So, where exactly are all of the electrons? Okay, so here we're going to get into some rules, all right? And for those of you that may be feeling very confused, try to sort of refocus again right now, because these rules are not that hard, and as long as you can learn how to apply the rules, then you're going to be just fine, okay? So, electrons exist in discrete energy levels. Each energy level has a number of different orbitals, okay? Orbitals are where you can actually find the electrons, okay? So like electrons occupy these things called orbitals, all right? They exist at energy levels, but each energy level has some different orbitals in it or associated with it, okay? So orbitals are important. Orbitals have two properties, and this is how you come up with the names for the orbitals, okay? You're going to have a number, which is the energy level, okay? So the energy level is going to be like number 1, number 2, number 3. That's going back to this, that's what this number is here, right? 1, 2, 3. What this says here is that generally like the lower numbered energy levels are closer to the nucleus, while higher numbers are further away. Okay, so if I were to ask you, okay, you've got an electron in energy level 1 and an electron in energy level 3, which one is closer to the nucleus? It would be number 1. Okay, so like as you get higher and higher in that number, that just means generally further and further away from the nucleus. Orbitals also have a type. Okay, so there are 4 different types of orbitals. There are s orbitals, p orbitals, d orbitals, and f orbitals. Okay, so you can have a 1s orbital. Okay, so that would be an s type at the first energy level. You could also have a 2p orbital. Okay, that orbital would be of a different type. It's like a p-type orbital, and it's at the energy level 2. Okay, you could also have a 2s orbital. Okay, so there's different energy levels, different types. These different types, the only thing that's different between these types are the shape, which essentially means how many electrons can fit there. Okay, so s orbitals can hold 2 electrons, p orbitals can hold 6, d orbitals can hold 10, f orbitals can hold 14. Those of you that like patterns will probably notice that the difference between each of these types is the number 4, right? So if you add 2 plus 4, you get 6, 6 plus 4, you get 10, 10 plus 4, you get 14, okay? So what I'm about to show you are some pictures of what these different orbitals look like. Don't freak out, okay? I don't need you to know any of what you're looking at right here, okay? I'm just showing you this because I think it's interesting, and you know, some of you that will move on to take AP Chemistry will need to learn a little bit more about this next year. These are the different types, okay? And essentially the types correspond to different shapes, okay? This right here is an s orbital. It's like a sphere. The p orbital is actually composed of like 3 different well, it's hard to explain, but three different orientations. Okay, one that's in like the x-axis direction, one in the z-axis direction, one in the y-axis direction. These are d orbitals down here and then f orbitals down here, okay? Like I said before, don't freak out about it. I just wanted to show you what these different shapes are. These shapes basically represent where you could find the electron at any given time, okay? So there are these weird shapes. It's not quite like rings, okay? So rings are not exactly accurate, but the rings being energy levels, if we think of it just as an energy level, like an amount of energy, and then consider these different types and shapes, then we kind of get an idea of where the electrons are, okay? This right here is a list of all of the different orbitals that we're going to ever have to work with, okay? You'll notice that all of these on this left-hand column are s orbitals, then you have p orbitals, d orbitals, and f orbitals. If you look at it the other way, kind of like rows, then you'll see that in the first energy level, right, number 1, we only have one type of orbital, the 1s. In the second row, we only have 2 types of orbitals, 2s and 2p. In the third energy level, we have 3. In the fourth, we have 4, and then it kind of goes back. It's almost like a pyramid type thing. This diagram is what we're going to be using to figure out exactly where these electrons are, okay? All right, so here are some definitions for you if you're taking notes along with me or taking notes from the slides at a later time. Like I've said before, the electron configuration of an atom is a written description of the location of electrons inside an atom. The standard notation electron configuration, this is most important for us, is the long form of the electron configuration, which details the location of every electron in the atom. Basically, it gives us where are the electrons, which orbitals are they in, where are the electrons. And then there's this thing called the noble gas notation. We're going to talk about that in the next video. Okay, so I'm not going to talk about this right now, but we will next time. Here is what an electron configuration looks like. Okay, this is an example of a standard notation electron configuration. You're always going to have these orbitals, okay? So, for example, the 1s orbital, 2s orbital, 2p, 3s, 3p, 4s. And then you're also going to have a number that is written kind of like an exponent. It's not an exponent, so it's not math. This is not a variable either. Okay, so I know this kind of looks like math, but it's really not. Keep in mind, right, this is just the name of an orbital. It's the 1s orbital, meaning it's in the first energy level, and it's an s-type orbital. And then this number here is the number of electrons in that orbital. Okay, so when I say the electron configuration is 1s2, that just means that 2 of the electrons are in the 1s orbital, okay, and so on and so forth. All right, so what we're going to do is we're going to learn how to write this type of thing for any given atom, okay? Like I said, it's actually not that hard. The rules are way less complicated than some of the other things I've been talking about today, okay? So let's actually do this, okay? And so I'm going to go zoom out here a little bit. And we are going to practice this. Now, this right here is that diagram I was showing you before. I'll bring up the big version of this. This is called the diagonal chart, okay? And this diagonal chart is actually all you need in order to do electron configurations, or in order to write them down, okay? Remember that the s orbitals, right, if I go back to this slide here, the s orbitals can all hold 2 electrons each. Okay, that's their maximum size. Think of it as like a basket, right? And you can't fit any more than 2 electrons inside of an s orbital. If you try to put a third one in there, you can't. There's no room. Okay, same thing with p orbitals. They can hold 6, d orbitals can hold 10, f orbitals can hold 14. Okay, and if we look at this diagram again, they're sort of arranged in this column structure here, right? So all of these guys can hold 2 electrons each. These can hold 6 electrons each. These can hold 10 each, and these can hold 14 each. So let's take a look here at the first few elements on the periodic table, and I'm going to show you how to write their electron configuration. Where are the electrons that are in these different elements? Okay, so we're going to start with the most basic example, hydrogen. Hydrogen is atomic number 1. And you'll recall that for now, we're going to assume that the atomic number, which is technically the number of protons, right, Well, we're also going to assume, at least for today, right, that is also the number of electrons. Okay? So hydrogen has one proton, also one electron, right, for a neutral atom. So we want to know where that electron is. Okay? What is the electron configuration for hydrogen? Where is it? Okay. If I go all the way back here and look at this little picture, let's talk about one last thing before we start doing those examples. Okay? Electrons are negatively charged. Okay? If you think back to before fall break, we looked at that table, right, that had all the properties of protons, neutrons, and electrons, the masses, the location. One of the things in that chart was the charge. Okay? Protons are positively charged, electrons are negatively charged. Neutrons are neutral. Okay? They don't have a charge. So the protons are here in the nucleus with a positive charge. Electrons have a negative charge. Okay? Naturally, opposite charges attract towards one another. Okay? So like positive things are attracted to negative things. If you were to let them go, the positive and negative things would move towards each other, right? So the natural place for an electron is to be as close to the nucleus as possible, okay? And as you can see here, that is the first energy level, right? That's the natural position that an electron would go to if it was allowed, okay? And for this example, for hydrogen, there's only one electron, right? So its natural spot is going to be in this first orbital, or in this first energy level. And in fact, that's what these lines on the diagonal chart are going to do for us. They're going to tell us the order in which these electrons go, okay? The way it works is you start at the top line, and you sort of go down, and when you hit an orbital, that is the first place that electrons go. So actually, every single electron configuration is going to start with 1s. There are always going to be electrons there, okay? In this case, we only have one electron, so the electron configuration, oopsie, is 1s1, okay? That is the electron configuration for hydrogen. And if we go back here, right, remember, so like this, for example, would be an electron configuration for a much larger element. For us, we have one electron. It's in the first orbital, which is the 1s orbital. Okay, so that's all I write, 1s1. Okay, some of you at home might be thinking, wow, this does not seem that hard. Well, let's see. Helium, 2 electrons. The electron configuration for helium would be 1s2. Okay, because I've got 2 electrons. And both of those electrons can fit inside of the 1s orbital, right? S orbitals can hold up to 2 electrons. Well, what if I have 3, right? So what if I'm talking about lithium now, right? An atom of lithium. How many electrons are there? 3. Well, can I put them all in the s orbital, in that first orbital? Am I allowed to do that? The answer is no, right? Because s orbitals can only hold 2 electrons. So this first orbital here, the 1s orbital, it can only hold 2 electrons. I can't write 3 there. Okay, that would be like breaking the rules. Okay, I can write 2. Okay, so I can put 2 electrons there. But now I have 1 electron left over. Okay, so where does that go? Well, that's what these lines are for here. Okay, so I can put 2 electrons in the 1s orbital. Now it's full, right? I still have 1 electron left over, right? Because I started with 3. So then I get to the end of the line, and I go to the start of the next line, go down, hit my next orbital, which is the 2s orbital, okay? And I have 1 electron left over, right? That needs a home. So that 1 electron is in the 2s orbital, right? The total number of electrons here should be equal to the total number of electrons that you have. So you're basically like adding up those little numbers, right? And you're going to be putting them in order according to this diagonal chart, okay? So here for the next one, this is going to be 1s2, 2s2, right? What would the electron configuration for boron be? 5 electrons here. Well, it's always going to start with 1s2. And then the next place you're always going to go, right, is 2s and once again, that's an s orbital, so I can only put 2 electrons there. The next place I would go, what do you think? Take a look at this. Orbital diagram here, or this diagonal chart. Where would I go after 2s? Well, there's really only 2 places you could think of, right? It's either 3s or 2p. And the way that you read this chart, when you get to the end of an arrow or the end of a line, you go to the beginning of the next line, the start of the new arrow. So after 2s, I actually am going to go up here at the start of the next line, and when I go down, the next place I hit is actually 2p. Okay? So 2p is the next orbital. How many electrons are in that orbital? Well, I have a total of 5 electrons for boron, and I've got 4 of them accounted for, so there's only 1 left that must be in that 2p orbital. Okay? So that is basically how it works, and you're just sort of repeating that process over and over again. It's not that bad. I'm going to save these next examples for us to do right after this video. Okay, and that is it for today. We're just going to be learning how to write these standard notation electron configurations using this diagonal rule chart. Okay? All right, thanks a lot for watching, and I'll be with you guys right after the video.